So predict the burst time of any process. So to predicting the burst time of any process, we have actually two methods. One comes into the category of a static method. And second is the dynamic one. Now let's talk about static and the dynamic. So what is in the static? In the static, we have two ways. The first is we can have the method of process size. Based on the process size, we can predict. And the second is the process type. Here in the dynamic way of finding out the burst time or the calculating the burst time, the first one is simple averaging. The first one is simple averaging, and the second one is exponential averaging. Okay, so we have two methods here in dynamic and we have two methods here in static. Let's talk about one by one. So the first one is process size. Now what happened in process size method? Now here it will look for the history of the process that is executed. Let's say we have a process which is some old process, and the size of this old process is, let's say, 100 KB, and it is taking around 50 milliseconds to execute into the CPU, which is a burst time. And this is the size of it, right? Now let's say a new process comes into the existence, and we know that how much time an old process has taken. The new process is also having approximate 100 KB of size. So what this model tells us that from the history, we find out that an old process having the 100 KB of size is taking 5 milliseconds of CPU time. So a new process, almost the similar size of size, can take almost 5 milliseconds for burst time. Okay. The same thing is actually not correct. Why it is not correct? Because the size cannot give you the proper burst time. There are many other properties or other thing that can affect the burst time. Okay. The reason is which type of process it is, how much IO it's required, what is the recursive function it is using, how much pointers it has already, what is the complexity of that particular program, how much loop it has. So all these criteria also comes into the picture when we do execute any process. So this particular method will not give you the accurate result, or not give you the result which we can use for the shortage of scheduling. Now the second type of method for predicting the burst time is process type. Now we have different types of process. Okay, so some of, let's say, we have some operating system based process, which is your system program or your scheduling algorithms or your process communication algorithms, or any type of operating system related programs. It comes under OS category of the program. Second category of the program is second category of the process is interactive. Now, what do you mean by interactive process? Let's say the gaming process, which is interacting with the user to give the input all the time. So these type of process comes under interactive process. Then we have some process which is called foreground process, which is running at up front, and you have to when it is going means we cannot run in the background, and some processes are running in the background. So there are different background processes like your firewalls, your, let's say, anti virus algorithms or antivirus functions, your network protocols, different networking protocols. So all those comes under the background processes which are running. Now, operating system related processes will take generally 3 to 5 unit of burst time. Interactive process will take around 5 to 8 unit of burst time in the Linux operating system. Now the foreground processes will take around 10 to 15 unit of time, and background processes will take slightly more than that, which is 15 to 20 unit of time of the CPU. So first what we do is, we first find it out which type of process we got. We classify into the category, and we'll say that it is taking that much of time. As you can say, it is not an exact time, it is an approximate time. So it may be 3, it may be 4, it may be 5, it is an operating system. It may be 5, it may be 6, it may be 7, or it may be 8 if it is an interactive type of process. For the foreground process, it will go from 10 to 15, and then there is a background process, it will go from 15 to 20. So it is not an exact burst time that it is provided. So if it is not providing the exact burst time, how we can calculate something related to in shortage of burst? So that is very tedious and very, you can say, not an implementable model. Again, the conclusion is that. Now let's talk about the dynamic type of model we have. So the first model in the dynamic type is simple averaging. Now what happened in simple averaging? In the simple averaging, let's say we have some processes P1, P2, P3, P4, and let's say it is a new process. Okay, and we know that P1 has taken T1 time, P2 has taken T2 time, P3 has taken T3 time, and P4 has taken T4 time. So what we do is we take the burst time of all the previous processes. We'll try to calculate the average of it, and whatever will come will give this particular value to the burst time of the new process. So this is a simple averaging algorithm. So if we'll try to make it, so it will go from 1 by n, means n number of processes which has already been executed. Let's say the I is going from 1 to n, and what we are doing is we are just making a summation of all the time of I, right? So I will go from 1, so the first process is t1, so t1 time it will taking, second process is taking t2 time, then third, then fourth, up to n. It will go and divide by n. This will give you the burst time for the new process, but it is also not give you the approximate or near about solution. What is the reason? The reason is, let's say we have processes, the old processes which are running, maybe they have a smaller burst time, or they are in the category of OS type, let's say. So the OS type is taking very less time, and suddenly I got some background processes. So that cannot match it, right? So the averaging of all these OS based processes are, let's say, 4. And if it is a background process, so how much it is taking, you see. So 15 to 20, that cannot be achieved by this particular method, right? So that's why this is also not suitable for the prediction of the burst time. So there is a second model in the dynamic category. Why this comes into the dynamic? Because we don't know that what is T1, T2, T3 or T4 up to Tn for the older process, because it is keep on changing, because we don't know that at what time of period which particular process will come and how much time it is taking. So that's why it comes into the category of um, dynamic model for predicting the burst time. Next talk about the next burst time prediction model for dynamic category, which is called exponential. Averaging. So this is another averaging type of formula that we have to use. So what is that formula is? That formula is, if we want to predict, so the prediction will be symbolically represented as tau. In some book, it is epsilon. So it depends upon which book we are following. So sometimes the tau is epsilon. So it is expected, or maybe the expected time we can pronounce it. And this is also expected time. So expected time of, let's say, the new process, let's say n plus 1, which can be calculated as alpha into actual burst time of the previous process, which is n, plus 1 minus alpha into predicted time of the previous process. So this is how your formula look like. Are you getting it? So this is the time that we want to calculate for a new process that has just come. We know what is the previous uh, burst time of the previous process, and we should know the predicted burst time of the previous process. Okay, so this algorithm is predicting the new processes. Let's say previously we have used this formula for predicting the previous process, but we got the actual also and the previous also. So these two, if we know, then we can calculate the next predicted burst time of the next process. Here alpha is smoothing factor. Now what is a smoothing factor? This particular alpha, the value of this alpha is greater than 0 and it is less than 1. it is not exactly 0. If we'll make it exactly 0, we cannot calculate, this Tn will not come into the formula. It will be omitted. It will be into by 0. Or if we'll make it 1, then this particular time will not come into the formula, and this will be omitted from here because it is 1 minus 1, it will be again 0. So we cannot afford that. So generally, this is smoothing factor will be taken as a 0.5, or you can say 1 by 2. Okay, let's talk about this particular formula in detail. So let's say if you want to calculate the burst time of, let's say, my new process, which is fifth process. So I should know the burst time of the previous process and the predicted burst time of the previous process. So this is the actual burst time of the previous process, which is T4. And we have a predicted burst time of the previous process, which is tau 4. So if we know these two things, we can calculate the tau of the new process, which is process 5, which is this process. This is a process 5, right? So this formula will telling us like this. So if you want to calculate it, let's say if you want to calculate the tau of n, so how we can calculate? We can calculate with alpha into actual time of n minus 1 plus 1 minus alpha tau of n minus 1. So tau will tell you the predicted time of it. Let's say if you want to calculate tau of n minus 1 will be equal to alpha t of n minus 2 plus 1 minus alpha tau of n minus 2. Let's say I want to calculate this tau of n minus 2. So what is tau of n minus 2? Tau of n minus 2 will be alpha tau of n minus 3, t of n minus 3 plus 1 minus alpha and tau of n minus 3. Okay. Let's say that if we have n equal to 3, then what will happen? So the formula will be look like this. So I want to calculate, let's say the fourth let's assume that the new process is the fourth process. So it will be alpha of the actual time of the process 3 plus the predicted time of the process 3. What is the predicted time of the process 3? It will be alpha into predicted time of the process, actual time of the process 2, 1 minus alpha predicted time of the process 2. What is predicted time of the process 2? Will be actual time of the process 1 plus 1 minus alpha predicted time of the process 1. So in this formula, what we should know? We should know that all the previous process, let's say P1, P2 and P3, how much burst time they have taken. Let's say they have taken 2, 3 and 4 burst time. And we should know one more variable, which is called predicted time of the first process. Let's say it is 3. So this thing and all this thing we should know, then only we can predict the predicted time of the process 4 that we can calculate. Because we know the predicted time, the burst time, actual time of these, the predicted time of the previous one, the very first process, then only we can calculate the new process predicted time. Okay. Now to understand this, let's have some examples so that you can understand this particular exponential averaging algorithm. Let me tell you, this exponential averaging algorithm is the best suited way of algorithm till now for predicting the burst time. If it doesn't have, you can say, we doesn't have the more refined version of the algorithm which can predict the burst time for any process other than this exponential averaging. Let's see some of the example related to this. So we have an example, and the alpha value here it is given is 0.5. Let's say the first time is, let's say, 5. Predicted burst time is 5, which is given. Now we have some process and its actual burst time, which is given. So we have a process, let's say P1, P2, P3, and P4. So we have, let's say, 4 processes. The burst time will be 4, 8, 5, and 6. Now, what is our task? Our task is to calculate predicted time of process 5. That is our objective. Okay. The calculate the predicted time of process 5. So process 5, what will be the time that we need to calculate? So we'll use the exponential averaging algorithm and we'll try to calculate it. Now, what is the formula? The formula is for tau n plus 1 means the predicted time of n plus 1. We have alpha into actual time of the previous process, which is n, plus 1 minus alpha, the predicted time of the previous process, which is n. So in this particular formula, if we'll fit it, this particular this particular formula will be fitting into this particular problem. So it will be predicted time of process 5 will be calculated as the alpha value is 0.5. So it will take it as a 0.5 into what is Tn? Tn is here 4 because we are talking about Tn plus 1 is 5. So Tn is 4 plus 1 minus alpha will be again 0.5 because 1 minus 0.5 is again 0.5 into this Tn. Now here, if we'll calculate, it is 0.5 into what is T4? T4 is 6. It will be 6 plus 0.5 into Tn, tau 1, because tau 1 is unknown to us. Okay, so this is actually not tau 1. We can say it as a 4, tau of 4, right? So in that method, if we'll calculate, so what is tau of 4? It will be 0.5 into time of 3, third process. So what is the actual time of third process is 5 into 5 plus 0.5 into tau of 3 because we don't know what is the value of tau of 3. It is not given here. Now what is tau of 3 will be 0.5 into what is the second one is 8 plus 0.5 of predicted time of 2. What is the predicted time of 2? It will be 0.5 into the P1, which is 4 plus 0.5 into tau of 1. What is tau of 1? It is already given 5. So we'll make it into 5. Now, from here, if we'll calculate what is the value of tau 2, so in the calculation, you will find out it is 2 plus it is 2.5, right? So 2 plus 2.5, it will be 4.5. Now this 4.5 will be added, will be put it here. It will be 4.5 into 5 and 8 into 0.5. So it will be 4 plus it will be something 2. Around 25. So it will be 6.25. Now this 6.25 will be added here. It will be 6.25 into 0.5 and 0.5 into 5. So it will be 2.5 plus it will be around 3.625. It will be 5.625. Then this value will be put it here instead of tau 4. it will be, and it will be 3. So 3 plus around 2 point something, it will be 5.81. So this is the actual answer. This is your answer. So 5.81 is the predicted time. This is 5.81 is the predicted time for process 5. Right? So this is the way how this exponential averaging methods for predicting the burst time is actually works. Let's see another example. That is your homework that you have to do. So the alpha value is 0.5 again. The tau of 1 will be, let's say 5 again. We have process and we have burst time. So we have process P1, P2, P3 and P4. What is our objective? Our objective is to find out the burst time of fifth one. The burst time here is 4, 8, 6 and 7. Now this is your problem. Now what we have to calculate? We have to calculate the predicted burst time of the fifth process. So that is, we have to calculate. So I think with this particular formula, you can put the values and you can get the predicted burst time of process 5. Yes. So this is how it will be done. So I think you understood the flow here. So in the previous algorithm, we have seen first come, first serve, which has the criteria of arrival time, and it comes into the category of non-preemption. If the arrival time is the same, which is a tiebreaker, so the tiebreaker is process ID, is the tiebreaker for it. Now in the second algorithm, which is the problem of the first come first serve, which is a convoy effect, the solution we thought is shortage of first algorithm might be the solution. Here, what is the in which, based on which criteria the first this shortage of first works is the burst time. So if the burst time is same for two processes, then arrival time will be the tiebreaker for that. And it comes into the category of, again, non-preemption algorithm. Non-preemptive algorithm. Now here also we have the disadvantages. The first disadvantage is here in some criteria, in some of the problems, we find out the convoy effect is still exists. The second problem is to finding out the burst time. For the burst time, we have method which is called in the dynamic model, we have the method exponential averaging. So generally we use exponential averaging to finding or the predicting the burst time of the process, which is actually not exact, but somehow it is giving us the near to right answer. So we use it. The first problem is the convoy effect. So to reduce the convoy effect, the third algorithm that we'll use is called shortest remaining time first. Now, this shortest remaining time first has again the criteria. The criteria is the burst time, which is same as shortage of first, but it comes into the category of preemptive scheduling. Here also the tiebreaker is the same, arrival time. We'll see that when we need this tiebreaker in this particular scheduling algorithm, but it comes into the category of preemption. Now the next scheduling algorithm that we are going to learn, which is called shortest remaining time first, is a preemptive scheduling algorithm. What is the meaning of preemptive scheduling algorithm? As I told you, if a process is running into the CPU and we find out that another process is there in the ready queue, which has more priority that may come into the CPU. So the previous process which is running in the CPU will be forcefully deallocating the CPU and will put onto the ready queue or the ready state, and the process that has the higher priority will be allocating the CPU. This is the one criteria. The second criteria may be the time quantum will be finished for the process which is running into the CPU. So we give another chance to the next process for the time quantum. Here in this particular shortest remaining time first, we always have to see the burst time. So here the priority is the burst time. So the process, if we'll find out there is a new process that has just come up and that new process has less burst time. So what we do is we remove the process which is running right now having the more burst time and put it into the ready queue, and we allow the new process which has the least burst time right now, and we allocate the CPU to that particular process which has the shortest burst time. So that is the criteria for the shortest remaining time first scheduling algorithm.